Hello, my name is Ghazaleh Torabi. I'm a master's student at Concordia University, and I will be presenting our paper titled Joint Detection and Activity Recognition of Construction Workers using Convolutional Neural Networks. I'll start with an introduction on why do we want to apply activity recognition on construction workers, followed by a short review of the previous studies on this topic. Next, I'll present our method, the results, and finally, a summary, conclusions, and future work. Construction labor productivity is much lower than the other industries. This causes budget and schedule overruns. As labor costs can amount to 50% or even more of the total project cost, it is crucial to improve labor productivity and therefore reduce the labor costs, reduce the duration of the project, and increase the savings at the end. Worksite monitoring for productivity analysis is still being done manually on most construction sites. In the traditional approach, supervisors keep track of the activities on the site through manual observation. They take surveys and interview project teams to make sure they're running on schedule. These approaches are error-prone, they are time-consuming, costly, and therefore aren't done frequently or timely enough to be used for effective and on-time decision-making. One way to automate this process is by using computer vision. Automation helps with providing timely information about status of operations on the site, helps with efficiently documenting the work progress and workers and equipment behavior and productivity. As a result, it will allow project managers to identify the delays and inefficiencies on time and make the right decisions to improve the situation. One of the promising and popular approaches used by multiple previous studies is what we refer to as the three-stage method in our paper. The term three-stage is used because the method consists of three main modules: detection, tracking, and activity classification. The method starts with a module to detect every worker in a frame. It then tracks them for a short period of time, for example, 3 seconds, and then finally crop the videos around the smallest box that contains all of these tracked boxes and passes the resulting clips to a third module to classify their activities. Different studies use different variations of this method, starting from simple modules to more advanced ones for tasks such as workers' work sampling, workspace planning, activity recognition of workers in groups, and also for productivity analysis of excavators. There are a few limitations to this approach. First, the previous studies only used clip or segment level annotation and evaluated their method at this level as well. What I mean by clip or segment level annotation is that the training and testing videos were short single worker clips that were manually trimmed around a single activity. And therefore, the annotation of the dataset was a single label corresponding to the activity of each clip. The issue with this type of annotation and evaluation is that when you apply this method to a continuous long video, the method automatically segments the video into short video clips. However, there is no manual supervision to make sure each video clip contains only a single activity anymore. Despite using short durations for these clips, they can still contain frames from the ending of one activity as well as the beginning of another one. So assigning a single label to the entire video clip introduces a frame level errors, which should be evaluated to get a good understanding of the performance of the model in a real world situation. Another issue is that each of the three modules are optimized separately, which does not guarantee the optimization of the entire method. In addition, error propagates from the previous modules to the next modules and degrades the overall performance of the method. Finally, the activity classification module only has access to the information inside the crop boxes and has no way of using the contextual information from around the workers in the full frames. To address these limitations, our objective was to apply a fully optimized method called YOWO that consists of a single module, uses context, and is trained and tested at frame level. We also improved the detection performance of this method because cameras are usually placed at a height to have a large field of view of the entire construction sites, and therefore workers appear very small in the frames and are hard to detect. A sensitivity analysis is also performed to compare different variations of YOWO and its improved version, which we call YOWO 53 in this paper. Our objectives can be realized in 3 steps: dataset preparation and annotation, activity recognition, and finally, performance analysis and comparison. Each of these steps are introduced in the next slides. As we wanted the method to be trained and evaluated at frame level, we needed a video dataset of workers and construction sites with labels for each worker and for each frame. And by labels, I mean boxes around each worker, as well as a label for each box corresponding to the activity of the worker inside the box. If we extract the frames from even a small number of short videos, we're left with thousands of video frames that are very hard and time-consuming to label manually. So we came up with a semi-automatic annotation framework to reduce the manual effort. In this framework, we first temporarily trim the site videos around activities of interest and extract the video frames from these clips. We then manually annotate a subset of these frames with boxes around workers and train an object detection model called faster CNN using this subset. We then apply this train model to detect the workers in the remaining frames. So using this approach, the task of drawing boxes around workers is automatically done, but we still need to label them with their corresponding activities. Some of the videos contain only a single activity. These videos can be labeled automatically. We use a simple tracking approach for the remaining videos that contain multiple workers doing different activities. We only label the boxes in the first frame of each video clip, and by comparing the intersection or reunion of these boxes to the boxes from the next frame, we identify the same worker and assign the same activity label to their boxes as well. Of course, there will be some errors and someone still has to manually go through the data set and to fix these errors, but still is much less time consuming compared to manually annotating the entire data set. The next step is activity recognition. YOWO and YOWO 53 models consist of two streams or branches. One is for extracting spatial features from a single RGB frame, and it helps for detection. It uses a 2D CNN in the 2D backbone block here. The next one is for extracting spatial temporal information from a stack of consecutive frames, which we're using 16 here, and it helps with activity classification. It uses 3D CNN in this 3D backbone block. The network then fuses these two outputs together and process them through some additional convolutional layers, and finally outputs bounding boxes as well as activity labels for each worker. So the main difference here compared to the previous studies is that the detection and activity classification are done at the same time. Therefore, it doesn't have the issue of propagating the error. The method is fully optimized and trained and tested end to end. Both detection and activity classification modules have access to the area around workers to make better prediction. Also, the data set is annotated at frame level and the method is evaluated at this level as well. YOWO 53 was proposed to improve the detection performance of the model because workers usually appear very small in the frames and are hard to detect. The original YOWO used a network called Darknet 19 in the 2D backbone block, but this network is not very accurate in detecting small objects. It is fast, but not good with small objects. The network was improved later to Darknet 53 by the original authors. Darknet 53 is slower, but better in detecting small objects. So we use Darknet 53 for YOWO as well, resulting into YOWO 53. For comparison, we tested YOWO and YOWO 53 models with different 3D backbones. We used two different networks, ResNex 101 because of its accuracy and ShuffleNet V228 because of its speed. We use 4 different input sizes for sensitivity analysis and evaluate the performance of the model at frame level using 3 different metrics: classification accuracy, detection recall, and F1 score. In addition to the frame level evaluation, we also evaluate the spatial temporal performance of the model using video mean average precision metric. This metric shows how good the model is in separating the temporal boundaries of the activities as well as the spatial boundaries of the bounding boxes. Our data set consists of 6 different activities. Some are non-value adding activities such as standing and walking, and some are productive activities such as transporting, hammering, drilling, and placing or fixing reinforcement bar. The table shows the statistics of the data set. The video frame sizes are 1,440 by 720, and we extracted them at 15 frames per second. The training set consists of 225 video clips, and the test set consists of 140 video clips. The results for the detection recall are shown on the left. Generally, increasing the size helps with the detection recall. We can see that YOWO 53 is doing better than YOWO for all input sizes. However, it operates at a lower speed compared to YOWO. There's also a slight improvement in most cases in the classification accuracy on the right when using YOWO 53. The speeds shown here are achieved by using the maximum batch size that we could fit in a single 32 gigabyte NVIDIA V100 GPU. The smaller the input size, the higher the batch size, and therefore the higher the speed. Note that for Resnick's model, we only trained and tested the models for the smallest input size due to GPU memory limits, but the same pattern holds for these models as well. The F1 scores of the models are shown on the left. This metric considers both detection and classification performance. As shown in the plot, the F1 score for YOWO 53 is generally higher than a YOWO. The difference becomes more apparent when the input size is smaller, because the smaller the input size, the harder it is to detect small objects such as workers. For video mean average precision, YOWO 53 is again doing better than YOWO for most cases, except for this exceptional situation of 896 by 896 input frames, which is 1% lower for YOWO 53. The general pattern seen here is that when the input size gets smaller, the speed increases and the performance drops. However, YOWO 53 is more robust to the input size compared to YOWO due to better detection performance. So these are some of the sample outputs here. Workers are placing or fixing reinforcement bars and walking. Here they're drilling and hammering. To summarize, in order to address the limitations of the previous studies, we applied and improved YOWO to jointly detect construction workers and classify 6 different activities. These models are fully optimized. They use full frames as the input, and therefore context around workers can be used to improve the activity classification performance. There is no limitation on the number of workers in the frames, and they can switch their activities continuously. The annotation and evaluation is done at frame level and therefore gives a better understanding of the performance of the model in a real-world situation. In the future, YOWO and YOWO 53 can be applied to other resources such as excavators. So in order to analyze the productivity of workers, we need to recognize and compute the duration of larger scale tasks such as formwork assembly instead of short atomic activities like transporting or hammering, which was done in this paper. However, these atomic activities can be combined to recognize the larger scale tasks which we're interested in for productivity analysis. Thank you for your attention. Please feel free to contact Professor Amin Hammad for any questions regarding this paper.